005 Welcome back to Science Click, where we dive into the wonders of the universe. Today, we're embarking on a thrilling journey to explore the tiniest building blocks of everything around us, quarks. 010 These elementary particles are the smallest pieces of matter we know, so minuscule they can't be broken down any further. Imagine them as the cosmic Lego bricks that form everything, from the atoms in your coffee mug to the dazzling galaxies swirling in the night sky. Isn't it mind-boggling to think that something so small holds the key to the vast universe? 018 Quarks are the foundation of reality as we know it. They're not just one type of particle but come in 6 fascinating flavors: up, down, charm, strange, top, and bottom. 034 Each has its own unique personality, and their differences shape the world we see. Let's dive deeper into what makes these quarks so special, shall we? 042 First, let's talk about their mass. Picture quarks as tiny cosmic weights, some light as a feather, others heavy like a boulder. The up and down quarks are the lightest of the bunch, requiring just a whisper of energy to come into existence. 056 This makes them incredibly stable and, no surprise, the most common quarks in the universe. They're the reliable workhorses, grouping together in trios to form protons and neutrons, the very core of every atom. 110 Without these lightweight quarks, the atoms in your body, your phone, or even a distant star wouldn't exist. 118 Next up are the charm and strange quarks, which are dozens of times heavier. And then, at the top of the scale, we have the top and bottom quarks. The top quark? It's a true heavyweight, over 70,000 times more massive than the up quark. 131 Because of their enormous mass, these 4 heavier quarks are rare, like exotic gems in the cosmic treasure chest. 139 Creating them demands an immense surge of energy, and they're so unstable they vanish almost as quickly as they appear. You'll mostly find them in high-energy particle colliders, where scientists spark them into existence to study their fleeting lives. 150 Isn't it incredible how much energy it takes to glimpse these elusive particles? 201 The second captivating trait of quarks is their electric charge. Unlike other elementary particles, which carry a whole charge, 0, +1, or -1, quarks are rebels. 222 They carry only a fraction of a charge. The up, charm, and top quarks hold a +2/3 charge, while the down, strange, and bottom quarks carry a -1/3 charge. 236 This fractional charge makes quarks utterly unique. But here's the catch: quarks never go solo. They always team up to form groups with a whole electric charge. 305 Take a proton, for example. It's made of 2 up quarks and 1 down quark. Their fractional charges, +2/3, +2/3, -1/3, add up perfectly to a +1 charge. 315 AM Neutron, on the other hand, has 2 down quarks and 1 up quark, balancing out to a neutral 0 charge. 327 It's like a cosmic math puzzle, perfectly solved every time. 03:3 Now, here's where things get even wilder. For every quark, there's an antiquark, a mirror image twin with the same mass but an opposite electric charge. 343 These antiparticles are the building blocks of antimatter, a mysterious counterpart to the matter we know. Quarks and antiquarks often pair up in nature, canceling out their charges to form neutral groups. 404 Imagine a dance between matter and antimatter, twirling together in perfect harmony. What a cosmic spectacle! For 13 Finally, the most intriguing quirk of quarks is their color charge. No, this isn't about rainbows or paint swatches. For 22 Physicists call it color charge, but it's just a playful name for a unique property. Quarks carry one of 3 colors: red, green, or blue, while antiquarks carry anti-red, anti-green, or anti-blue. 447 These charges have nothing to do with what your eyes see. They're a way to describe how quarks interact. In nature, quarks always group together to create a white or neutral charge. 524 Picture a proton with 1 red, 1 green, and 1 blue quark, blending together like light through a prism to form a neutral whole. 545 The same happens with a quark and antiquark pair, like red and anti-red, balancing out perfectly. 604 But here's the twist. color charge isn't static. Imagine a quark glowing red one moment, then, poof, it shifts to blue. 619 When this happens, the quark releases its red charge as a new particle called a gluon, which carries the red charge and an anti-blue charge to balance things out. 637 This dynamic dance of color charges keeps the subatomic world buzzing with energy. Curious about how gluons and quarks keep this cosmic ballet going? Let's turn the page to explore the forces that bind them together and uncover more secrets of the subatomic universe. 647 Let's dive back into the mesmerizing world of quarks, where the dance of particles never stops. Last time, we uncovered how quarks carry a mysterious color charge, red, green, or blue, and how gluons, those cosmic messengers, carry both a color charge and an anti-charge, like anti-red, anti-green, or anti-blue. 653 Picture gluons as vibrant sparks flying between quarks, orchestrating a dazzling exchange of colors that keeps the subatomic world in motion. But how does this colorful exchange actually work? 7 o'clock Imagine two quarks nearby, one glowing red, another shining blue. When the red quark releases a gluon carrying its red charge and an anti-blue charge, something magical happens. 706 The blue quark absorbs this gluon, and in a flash, it swaps its blue hue for a vibrant red. 714 The red quark, in turn, takes on the blue charge. It's as if these quarks are playing a cosmic game of tag, trading colors in an instant. 722 In the universe, these gluon exchanges happen constantly, with quarks swapping colors like dancers twirling across a stage. Isn't it wild to think that the building blocks of matter are in such constant flux? 731 This colorful interplay isn't just for show, it's the glue that holds quarks together. Picture quarks linked by an invisible elastic band, stretching and pulling as they move. 740 If you try to pull one quark away from its partners, the band tightens, and the attraction grows stronger, like a rubber band stretched to its limit. 750 This powerful force is called the strong interaction, one of the four fundamental forces that govern the universe. 8 o'clock It's the cosmic superglue that keeps quarks bound together, ensuring the stability of protons and neutrons, the very foundation of atoms. Without this force, the matter that makes up stars, planets, and even you would simply fall apart. Can you imagine a universe without this invisible bond? 817 But here's where things get even more intriguing. The strong interaction has a fascinating consequence called color confinement. 822 Quarks are social creatures. They're never found alone. Let's say you try to isolate one quark from a proton, like pulling a single thread from a tightly woven tapestry. 831 As you tug, the attraction between the quarks grows stronger, much like that elastic band resisting your pull. 838 If you pull hard enough, you might break the quark free, but the universe has a trick up its sleeve. 846 The moment you separate the quark, the energy stored in that stretched band snaps, transforming into a brand new quark-antiquark pair. 856 Suddenly, your isolated quark is no longer alone. It's paired with a new antiquark, like a cosmic partner appearing out of nowhere. 909 This phenomenon, color confinement, ensures that quarks are never solitary. They're always part of a group, whether in protons, neutrons, or quark-antiquark pairs. 916 It's this rule that keeps the nuclei of atoms stable, holding together the matter that forms everything in the universe, from the tiniest speck of dust to the grandest galaxy. 928 Isn't it astonishing how such a small particle can have such a profound impact on the cosmos? But the story doesn't end here. What other forces and particles work alongside quarks to shape our reality? Let's turn to page 3 to uncover the next chapter in this cosmic tale. 404 Welcome back to our cosmic adventure on Science Click. We're deep in the subatomic realm, where quarks and their quirky traits continue to captivate us. Last time, we explored how quarks and antiquarks pair up to form groups with a neutral electric charge, like a perfectly balanced dance. 409 Now, let's shine a spotlight on the most fascinating feature of quarks, their color charge. Picture a vibrant, invisible force that binds the building blocks of the universe in a dazzling display. Ready to unravel this mystery? For 18 Unlike the electric charge, which is simply positive or negative, Color charge is a whole new kind of magic. For 25 quarks carry one of 3 colors, red, green, or blue. Don't be fooled, these aren't colors you'd see in a rainbow. For 39 they're just playful names scientists picked to describe this unique property. Each quark in the universe proudly wears one of these charges, while their anti-quark twins sport the opposites, anti-red, anti-green, or anti-blue. 503 it's like a cosmic costume party where every quark and anti-quark has a matching yet opposite partner. 514 here's where it gets exciting. When quarks team up, their color charges combine to create something special, a white or neutral charge. 519 imagine 3 quarks in a proton, 1 red, 1 green, 1 blue, blending together like light through a prism to form a perfect, neutral whole. 524 the same happens with a neutron or a quark-anti-quark pair, like a red quark and an anti-red quark, canceling each other out to form a neutral charge. 535 in nature, quarks always group this way, ensuring their total color charge is white. Isn't it incredible how these tiny particles maintain such perfect harmony? 604 but the story of color charge doesn't stop there. It's dynamic, ever-changing. Picture a quark glowing red, pulsing with energy. 613 thanks to the wild rules of quantum mechanics, it might suddenly shift to blue. 619 when this happens, the quark releases its red charge in the form of a gluon, a tiny particle that carries the red charge and an anti-blue charge to balance the shift. 634 gluons are like cosmic couriers, zipping between quarks to swap colors in a never-ending game of tag. 647 every gluon carries a color charge, red, green, or blue, paired with an anti-charge, ensuring the subatomic world stays in balance. 7 o'clock let's zoom in on this process. Imagine a red quark sending a gluon to a nearby blue quark. 704 when the blue quark absorbs the gluon, transforms, shedding its blue charge and taking on the red hue. 712 meanwhile, the original red quark turns blue, as if they've swapped costumes in a split second. 720 this constant color swapping, driven by gluons, isn't just a quirky trait, it's the heartbeat of the strong interaction, the force that binds quarks together like an unbreakable cosmic thread. 734 this force ensures quarks stay close, forming the protons and neutrons that hold the universe together. Can you picture the invisible ties that keep the stars and planets in place? 8 o'clock as we've seen, the strong interaction is one of the 4 fundamental forces ruling the cosmos, and its effects are profound. But there's more to this tale. Color charge sets the stage for an even deeper mystery. What happens when quarks interact with other forces, or when we try to peer even closer into their world? Let's turn to page 4 to explore the next chapter of this subatomic saga.